So this is going to be a sort of conceptual introduction to regression analysis, which is a tool that gets used by social scientists for a variety of things. We've been talking a lot about how to achieve statistical control, to be able to sort of parse out cases that maybe aren't exactly similar, to kind of find that similarity. And regression can be a powerful tool for helping us to achieve statistical control, but it also has an advantage to allow us to make forecasts. And this is one of the things that makes it so widely used, not just as a tool for academics who are testing hypotheses, but also for business managers who are trying to forecast future events, or for analysts who are trying to pick up future trends. And so we'll talk a little bit about what regression does, how to interpret the results, and then what this idea of multiple regression looks like, so that we can kind of understand why this is such a powerful tool for telling interesting stories. So I'll begin with just the sort of basic example of the scatter plot here, where we have the corruption perception index from Transparency International, which has higher scores being better, less corruption, lower scores being worse, more corruption, and then GDP per capita in thousands, sort of along the x-axis. And if we look at that, we can sort of see a scatter plot of where these points fall. But if you were to just ask me, I'm thinking of a country, what do you think their corruption perception index score would be? I would probably guess somewhere around 4, because 4 is the average value for countries in terms of their corruption perception index. But the average is actually a pretty terrible guess, because there's a lot of countries that are above 4, a lot of countries that are below 4. And while I think without any information, that's a reasonable place to start, we can probably do a lot better, particularly if we think about the relationship between GDP per capita and those corruption perception index. And so the mean is maybe not the best way to think about how to make a prediction about a country's corruption perception index. But if we use those two things together, we can draw a similar line that kind of cuts through the middle of those points. And that does a better job with a forecast, with a prediction. And so the idea with this line, with this slanty line, is that if you tell me to make a prediction about a country's corruption perception level, I will counter by saying, all right, can you tell me something about their GDP? And if you say, well, they have a low GDP per capita, like 5,000, I would say, oh, well, I bet it's under 4, maybe 3. Right? Because I know that that's kind of how that line looks. If you say they have a high GDP per capita, maybe 30,000 or 40,000, I'd say, oh, I bet it's higher than 4. I bet it's 6 or 8. So we're essentially using that correlation, and we're using what we sort of know about that correlation to try to make a more informed prediction, or a more informed guess. Well, then the question becomes, so how do we know what line to draw through the center of those points? What makes for a good line? And so one way to think about this is to think about how much better the slanty line does than the average. And so I just kind of zoomed in a little bit for this picture here, and kind of separated out the distance between that overall average, that sort of first uninformed guess, and a point. And note that there's a part of that distance that we're able to explain with that line, with that new slanty line. And that's sort of the green section. That's like the gain, the improvement that we've got. But that improvement isn't perfect, right? Not every point is hitting that slanty line perfectly. And so there's still that gap that we're not explaining. There's still that blue distance that is unexplained variation. And so when we're looking to draw a line through a collection of points in a scatter plot, what we would call the regression line, we are looking for the line that has the smallest collective amount of blue, of that unexplained variation. And so across all of the points in our data set, we would look for the line that minimizes those blue areas, and then we would say, aha, this is the best, most efficient line we can draw through this set of points. And that's our regression line. Okay, so if we have this idea of a regression line, that we're drawing a line through a bunch of points that does the best job possible at explaining the variation we see in that scatter plot, then that comes to the next question, which is, so how do we think about that line, or how do we communicate that line? And if you go back to sort of maybe high school algebra, you may recall that we can create an equation to represent a line. And so that equation has an x value and a y value, so the coordinate pairs. The y value is your output on your y-axis. The x is sort of the input value on your x-axis. And then we need two additional pieces of information. We need a intercept, the y-intercept, which is the a in this equation, which if I jump back here, this is where that slanty line crosses the y-axis, the intercept point. So it would be just below 2 in this particular equation for a line. And then we also have the slope, which is the rate of change. So you may recall rise over run. It's basically if you move over 1 unit in x, how much do you increase or decrease in your y values? And that's essentially the relationship that we're seeing between x and y. How much does a change in x impact y? And with that formula, like if you have those two pieces of information, if you have the slope and you have the intercept, you can draw a line, and you can draw that line through the center of your points, and you can use that line to make predictions, because if I know a particular x value, I can insert that x value into that equation and get a forecast or a prediction for y, which is kind of handy, and we'll talk about it in a little bit. But before I do that, I want to kind of highlight what we're talking about when we think about that slope or that rate of change. So a positive slope means that as we're moving to the right, on the x-axis, as we're counting up on the x-axis, we are also going up on the y-axis. And again, sort of be moving in a positive direction on x, positive direction on y. A positive times a positive is a positive. So it's a positive relationship. It's sort of slanting up and to the right. But we can also have negative slopes, right, where you move over to the right in the positive direction on x, and then you're going down in a negative direction on y. And so a positive times a negative is a negative relationship in your slope in that second graph below. But the value of the slope also tells us the steepness of that increase or decrease. So a larger value means that as you're moving over 1 unit, you're going up more. A smaller value means that as you move over 1 unit, you're going up just a little bit, right? So that slope can actually tell us a lot about that relationship between x and y, and it's something that we paid a lot of attention to when we're looking at regression results. There's one additional thing I want to flag here about these two graphs. The graph at the top, I mean, I think the line looks pretty good. Like, I think points are kind of clustered pretty closely at the start, and as you move sort of off to the right, things get a little bit, more scattered, but the line is doing a pretty good job cutting through the center of all those points. The line at the bottom, it's still the regression line. It's the line that minimizes the amount of miss in between the line and the points, but it's not really tracking with the points all that well. When I'm sort of just stepping back and looking at those points, I see sort of this curve shape relationship, but I see the line kind of cutting through it where it's maybe too low at the start, and then maybe in the middle it's a little bit too high. And so if I'm looking at that, I might say that equation of a line, that straight line, doesn't do a particularly good job matching to where those points are, because it's trying to stick with just a straight line. And at least when we start out with regression, we are working just with straight lines. It's possible to tinker with things later on and to bend the shape of that line to kind of match those points a little bit more closely. We won't get into that in this class or in this discussion, but a good modeler, a good analyst will take a look at the relationship between x and y and try to match it, not just in terms of here's a line, but here's a line that actually seems to correspond to the pattern that we're seeing in the data. Okay, so we've got an equation for a line. I can use that equation to make a forecast, right? If you tell me that a country's GDP per capita is 30,000, I could maybe go to this graph and find 30,000 on the x-axis and go all the way up to where my line hits, and then go all the way over and say, aha, my forecast, my prediction for a country with a GDP per capita of 30,000 would be 8, because that's sort of where it hits on the line. But you might follow up with a secondary question, which is, but how good is that forecast? Like, how confident are you that that's actually where things are? And that's a fair question, because even if I have a good equation for a line, even if it's the line that has the minimum amount of miss, there's still miss. And so maybe I want to be able to understand whether or not my line is doing a good job or a bad job at explaining these points. And we actually have a statistic that kind of helps us to get at that. It's called the R-square value. It's technically the square of Pearson's R, although we get to it by squaring those green and blue portions of the line, but I won't go into the math on it. It has a really simple, straightforward interpretation. It's the percent of the variation that we are explaining in our Y value given our X value. And so it has a very intuitive visual interpretation. If I look at the cluster of points in the line on the left, the lines cutting through the center of those points, it's the regression line, it's the line of best fit, but there's a lot of error. There's a lot of sort of points above and below, and maybe I would say that's not doing a great job of making a prediction of those points. Whereas the graph on the right-hand side, right, basically the same line of best fit, cutting through the points, but those points are packed in really close around the line. And so those points would have a larger R-square. That might be a 0.8, an 80% of variation explained, whereas the graph on the right would have a lower R-square. Maybe they're only explaining 20 or 30% of the variation in those points using that line. And so R-square ends up being a really intuitive way of sort of answering that question or communicating that answer to that question, which is how good of a job is your regression line doing at predicting or forecasting? How reliable should I take that? And we can look at the R-square and say this is doing a really good job. It's capturing most very,ation, R-square 0.7, 0.8, 0.9, or this isn't maybe doing the best. There's a lot of unexplained variation, 0.1, 0.2. Only explain 20% of what's happening. Okay, so as I mentioned, we can use the equation of a line to make a forecast, right? And so again, returning to high school algebra, if I give you an X value, you should be able to plug that into your equation for a line and say, okay, if X equals 10, well then 10 times 2 is 20. That's the slope piece, plus 3, my Y value is 23. And sometimes when we talk about this kind of forecast, what we're saying is that it is a forecast or an estimate conditional on or controlling for X. I know X, therefore I can make a better conditional forecast for Y using what I know about X and its relationship with Y. And so when we talk about those forecasts, that language sometimes is important to keep track of. But you may be at this point wondering, so, okay, I remember the college algebra or the high school algebra about, inputting X into a function and getting a Y value out. But how do I build that equation of a line? Where does that come from? Do I just have to eyeball that or estimate that? And the answer is no, you use Excel or you use SPSS or Stata or R or any statistical package, and they will generate for you a table of statistics that you can use to build that equation of a line. And so this is an example of the kind of output you would get if you ran a regression. I think it's actually the regression, or no, it's not the exact regression I was showing earlier. It's using GDP per capita, but I forget what the dependent variable is. You'll get a table of regression results that look more or less like this. Sometimes things are sort of shuffled around a little bit, but all the pieces are going to be in place for every statistical package. And so if you do a simple bivariate 2-variable X and Y regression, you will get a line for your X variable. So in this case, GDP per capita, and you'll get another line that sometimes is called constant and sometimes is called intercept. Maybe there's another name for it. Constant, intercept seem to be the two most common, which is essentially your Y-intercept value. And so if I go over from the labels to that first column of coefficients, this is the information I need to build the equation of a line. I have my Y-intercept, that's the 1.9, and I have my slope, which is 0.0002, which is a really small slope. But again, we're thinking about GDP per capita in dollars for this one. So, the effect of a single dollar probably isn't a whole lot, but the effect of 1,000 might be a noticeable impact or a noticeable change. So I have those two pieces of information and they're right there for me. And I could build my line. Y equals 1.9 plus 0.0002 times X. And if I plug in an X value, I should be able to get a forecast for Y. In these regression tables, you tend to focus, or I tend to focus, people tend to focus quite a bit on that coefficients column, because that's what tells you what that line is going to look like and helps you build it. But it's not the only piece of information that you need. As you may recall from our discussion of hypothesis testing, when we get values, statistical values, we oftentimes want to know, are these things just random sampling variation, or is this something that's likely to be real? And the way that we do that is by conducting a statistical test of significance. We look at standard errors, we calculate t-values, where we sort of place our coefficient on a sampling distribution placed at 0, because the null hypothesis is 0, and develop a p-value or a probability of that particular value that you found in your analysis happening by chance if the sampling distribution is centered on 0. And if it's less than 0.05, then we say, aha, this is unlikely to be just chance, and it's probably something real. That was a very rapid recap of hypothesis testing. If that seems a little bit intense, I have other videos that discuss hypothesis testing. But the short version is that we can just sort of skip to the end column, to the p-values, and look at those values and use those to get a sense of whether or not those coefficients that we're looking at are probably real, or maybe you're just sampling variation. And so the idea is that if your p-value is very, very small, typically less than 0.05, but we could set more rigorous threshold, 0.001 or so, then we can say with confidence that we're seeing a pattern, and that pattern probably exists in the larger world and is not just sampling variation. And so if I'm looking at the GDP per capita line and I'm looking at the p-values, I have a p-value of 1.7135 e to the -17th, which is kind of a weird number, especially when I was expecting a number between 0 and 1, because it's a probability. But I just have to recall that e to the -17 is Excel's way of writing scientific notation. And what that means is that I have this 1.7, and I need to take that decimal point and move it 17 spaces to the left, because I'm moving it negative in the negative direction. And when I do that, I end up with 0.16zeros1713. That's a really, really tiny number. The probability of getting a slope, a coefficient for the GDP per capita line by just random chance, if there's no relationship out there in the world, is infinitesimally small, like 1 in a trillion, or maybe even smaller than that. And so I can reasonably say this isn't just random variation. There's probably something there. And so when we're looking at those regression results, those are probably the two places that we look. We probably look at the first column with the coefficients to get a sense of what the line looks like. And we look at the last column at the p-values to get a sense of, is this just random chance, like a 0.7, where I could say 70% of the time this just happened by chance. It's not something to be taken seriously, or something like these results that are ridiculously small probabilities happening by chance. And then that can kind of give you a sense of whether or not you want to believe your model or trust your model. Okay, so I'm going to push forward with one more piece of this discussion, and that is multivariate regression. That one of the nice things about regression is that it allows us to tell more sophisticated, more complex stories about the world. And we do that by building a model, by saying, these are the various things I want to incorporate into my analysis, into my story of how the world works. And the way that we do that is by modifying the equation of a line slightly. And so at the bottom, I have sort of this messier looking thing. But if you just focus on the first maybe third of it, it's actually the exact same equation we were seeing before. It's y equals b sub 0, which is our intercept, basically. It's a coefficient, it's a value that doesn't have an x attached to it, the intercept, plus b sub 1 times x. So we've got a slope times an x. And if we just stop there, that's the equation of the line, and nothing's really changed. But we've added a second piece, which is b sub 2 times x sub 2. So what we're saying is we've got this equation of a line, but we're going to add in another x value variable, a second variable to help us tell the story. And that variable has a relationship with the y variable, our dependent variable. And that relationship is the second slope. And we could add in a third or a fourth or a fifth. We could just keep going and adding in variables, not indefinitely. We end up running out of cases where the math starts breaking, but we can add in multiple variables into our analysis, each of which has a relationship with the y value that's either going to push that y value, that prediction up, or it's going to push it down. And then there's this little piece at the end, this e, which is just a quick reminder that even if we build a good model, a good multivariate regression equation, it's not going to be perfect. In fact, it mathematically can't be perfect. If you get a perfect regression model, you end up dividing by 0 and math breaks. So it's not going to be perfect. There's always going to be a little bit of error. Sometimes cases are going to be just a little bit too high. Sometimes they're going to be a little bit too low. Sometimes you get a big error. And so there's this error term that sort of gets added on to kind of remind us, like, this is a model, this is a forecast, this is not reality. Okay, so what does this look like in practice? And I think I've got an example that maybe helps folks kind of wrap their head around it a little bit better. So this is a graph that I saw. It was put out by Gallup a number of years ago, and they were claiming in this article that emotional health is related to age, where as Americans get older, their emotional health goes up. And they measured this by the percentage of people who scored really high on their emotional health index. And so what they said is, look, young people seem to be in the mid-20s, old people seem to be in the mid-30s. Clearly, as you get older, you have better emotional health. I looked at that and said, well, maybe I could see it. And sure enough, I ran a regression, and this is sort of the top one, in which I took the values that they had and I plugged in the age categories, just the first year of those age categories, to kind of see, like, what's it look like. And if I look at those coefficients, I have an intercept of 21.7, which, is about where it would cross the y-axis. We can't actually see the y-axis here, but maybe that works. Age is 0.13. So every year older you get, your collectively our emotional health, the percentage of people claiming high emotional health, goes up by 0.13. So in 5 years, you get a 1% increase, or 6 or 7 years, you get a 1% increase. And we look at our p-values, and the values are small. They're less than 0.05. This is unlikely to just happen by chance. That seems like there's a relationship there. And I look at my R-square value, and it's 51.6% of the variation in this graph is being explained by that regression line. And so that's doing pretty good. And so I thought, well, maybe Gallup's onto something. And then I noticed that there seems to be a spike somewhere between 26 to 35, that like 10-point jump happens when people go between the ages of 60 and 70. And I thought, well, something's happening in there. Oh, people are hitting retirement. That makes sense. So you get a few people who go into early retirement, you have a few folks who work till they're 67, and a good chunk of people retire at 65. I wonder if all of this variation on age is really just a function of retirement. And so I ran that analysis, and I plugged in just a dichotomous variable for, are you likely retired? I think I used 0.5 for the 60 to 65 cohort. But what I found is that retirement variable, that equation for line starts at 25, and it just kind of plods along at 25. And then when you hit retirement, you get a jump up of 8.2. And that then just sort of plods along at that higher level. And my p-values, they're statistically significant. They're very, very small values. Very unlikely to find this pattern just by chance. It's probably explaining something that's out there in the world. And when I look at my R-square value, 0.857, I'm explaining 86% of the variation in that graph. And I'm doing a better job explaining that variation than I was when I was looking at just age, where I was only able to explain 51%. So I'm telling a better story using retirement rather than age. But when I go back and look at that graph, I actually see something different happening. What I see is initially sort of people are carefree and young in 18 age, and then maybe they get into the workforce or they have kids, and a chunk of the population sort of declines in their high emotional health level, and then they kind of plod along at sort of a steady level, and then people retire and they get this boost up, and people who are miserable with their work suddenly are not working anymore and they have higher emotional health, and that's great. And then as you get older, your spouse dies, your friends start dying, your body starts breaking down, and that takes a toll on emotional health. And so what I'm actually seeing is a pattern where as you get older, your emotional health collectively, or our emotional health declines. We get a boost up with retirement, but then it continues to decline again. And that's a more sophisticated story, but that's a story I can tell with regression. And so I plugged in both age and retirement into my regression equation. And so what I found is essentially that story I just told. You start out with the intercept of 28, almost 29, and every year that goes by, you see a little bit less than 0.1% decline. You have this negative effect from aging, which is contrary to what Gallup initially told us, but fits with that story. And so over time, people are sort of declining. And then you get a boost with retirement. You get a 12-point boost in the percentage of the population that's reporting high emotional health. But then it continues to decline as people get older. And this model, this more sophisticated story, has a better R-square. It has 0.9. We're explaining 90%, almost 91% of the variation in that initial graph, in that data. And we're able to do it in a way that tells a more sophisticated story, and it allows us to look at age conditional on other pieces of information. So I can look at the relationship between age and that emotional well-being percentage of the population that reported high. I can look at that relationship, and I can look at that relationship having taken into account whether you are retired or not retired. And so essentially we're creating more of an apples to apples comparison when we have a conversation about what's the effect of age on emotional well-being, which is helpful both from a perspective of nailing down causality, because we need to be able to create apples to apples comparisons, but it's also really important in terms of making forecasts. That if I have a model that has an R-square of 0.9 or 0.908, it's really good. That means that I can make a forecast. I can plug in, are you retired or are you not retired, and an age value, and get a pretty good sense of what that cohort is looking like in terms of emotional health based on this analysis. So regression ends up being a really powerful tool. It's used widely in academic and professional circles, and it's useful to have a sense of how it works and what it's doing.